Good morning, everyone. Thank you for joining us for Netted from Dripper Quality, the second in our series of webinars, part 2. I'm Jerry Austin. I'm a product manager, Netted from South Africa. We're coming to you from Kraaifontein, a factory in Kraaifontein, the Western Cape. I must apologize from the outset if you should hear some background noises. We're in an operating factory and warehousing. Apologize if you might hear occasional machinery or forklifts. In part 1, we looked at the turbulence coefficient. We saw that we needed to create pressure loss within a dripper, and pressure loss was a combination of turbulence and friction loss. We wanted more turbulence, less friction loss, and turbulence was measured by the turbulence coefficient, K. We said the greater the value of K, the cleaner the dripper. And the K, the turbulence coefficient, depends on the labyrinth depth, width, and length, number of teeth, and the design and manufacture of the labyrinth, including the teeth. And then we looked at the end of that webinar, the 4 remaining factors that we needed to look at that are given in all of the technical data that we give on our drippers. And what we're going to look at today is what we've on the right-hand side of the screen there in red, K, sometimes called A, and X, sometimes called B. We're going to look at what do these factors mean. In part 1, we discussed how dripper lines are pressurized. Look here, the pressure gauge, just like the anomaly that I used was the tire pressure. In a non-pressure compensating dripper, as the pressure at the inlet of the dripper changes, so too does its flow rate. The lower the pressure, the lower the flow rate, and the higher the pressure, the higher the flow rate. The relationship between these two is given by this equation. Q equals K times P to the power of X. Sometimes that is written as Q equals A times P to the power of B. They're always given as K and X, or A and B, in all of the literature that we give, the technical literature, such as encircled in the table above. Q is the flow rate. K is a constant, it's just a number. P is the pressure, and X is the exponent. Another word for exponent is to the power of. The dot, when we put a dot there, that dot is not a decimal point. It means multiplied by. If we put a time sign there, you could easily confuse it with the pressure exponent that's also called X. Q is a symbol always given to flow rate. And for small flow rates, we're talking liters per hour, such as with drippers. K is a number that is specific to each individual dripper. It's connected to the flow rate, but it's not too important for this exercise. And sometimes it's called A. But it's not to be confused with the turbulence coefficient K. It's also called K. I don't know why the two are called K. It's just the way they are. We mustn't confuse the two. P is the inlet pressure, and it's measured in meters. Now, meters measures the difference between 2 points, not pressure. So why is this not in bars? An irrigation designer uses meters of water to calculate all pressures. However, outside of engineering, such as a farmer, meters are not really necessary to measure pressure. It's probably a good idea that they're not used as a means of measuring pressure with a farmer. Just stick with bars or kilopascals. So what do meters of pressure mean? If we get a pressure gauge and we place it 10.2 meters below the surface of a small vertical pipe or a large vertical tank or a large dam reservoir, that pressure gauge will read 1 bar. Then, if the height of water in each of those 3 bodies of water, pressure gauge was now only 5.1 and the pressure gauge was placed at the bottom of all of them again, at the bottom of the small vertical pipe or a large vertical tank or a large dam, it will always read 0.5 of a bar, regardless of the size of the body of water. Okay? So the volume of water, whether it be big or small, it's got no bearing on the pressure. Pressure is purely related to the height below the surface. 1 bar is 10.2 meters, and we generally round that off to 10 meters. An irrigation designer's calculation need to combine water pressure with the differences in elevation in the irrigation system itself. So therefore, to combine the two, we do everything uniformly and we put everything in meters. What is important? This only applies to water. 10.2 meters height of another fluid, or even water containing a lot of dissolved fertilizer, will not produce 1 bar pressure. And for this reason, to avoid confusion, that's why I think we shouldn't really be talking about meters to outside of fluid mechanics. The components of an irrigation system comprise of a head control, followed by a main line, followed by irrigation valves, and then we've got sub-mains, and then we've got laterals with drippers in them. Now, an irrigation designer, when he starts a design, he starts with the dripper, and he designs backwards up this list until he gets to the pump at the very end. Okay, so we work backwards when we design an irrigation system. Now, as we discussed in part 1, as water travels down a pipe, it loses pressure. So on a flat irrigation block, the highest pressure will always be immediately after the valve, and the lowest pressure will be at the corners. So therefore, if the highest pressure is there with a non-pressure compensating dripper, the highest flow rate will be there, and the lowest flow rates will be there. The flow rate for every dripper may not vary by more than 10% across the entire irrigation block. So if we take a 1 litre an hour dripper, it can't vary by more than 10%. So that means we can go up 5%, down 5%. So if we take 1 litre an hour, you add 5%, you get 1.05 litres an hour. And if we get a 1 litre an hour minus 5%, then we get 0.95 litres an hour. So our maximum flow rate is 1.05, minimum is 0.95. So therefore, at the beginning, just after the irrigation valve, that's where our maximum flow rate will be, 105 litres an hour, and then the last drippers at the end will be 0.95 litres an hour. Now, let's take the exponent. The exponent means to the power of. Just do a bit of maths here just to put things in basic terms. 3, and going in the box on the left there, in the top left, 3 to the power of 2 is written as 3 with a little 2 up in the top of it. So that means 3 times 3 equals 9. And then when we go in reverse, the square root of 9 is that little V sign next to the 9, and that equals 3. Now I go to the middle box. 9 to the power of 0.5 equals 3. So you can see that 9 to the power of 0.5 and to the square root, they're the same thing. So the power of 0.5 is the same as the square root of. Now we go to the right-hand box. The exponents of drippers always vary generally between 0.5 and they come down to 0. Okay, generally you won't get an exponent higher than 0.5. And the last thing that I want to make note of here, anything to the power of 0 equals 1. So 10 to the power of 0 equals 1, and 25,398, any number getting to the power of 0 equals 1. In our dripper sample, if x is to the power if x is 0.5 and k is 0.316, and if we take the pressure as 10 meters and multiply that out, we will get 1 liter per hour. The nominal flow rate of all netafilm drippers is always the flow rate at 10 meters. So in our sample dripper, we have P is 10 to the power of 0.5 times 0.316 equals 1 liter per hour. Now, how to use the pressure exponent ourselves? Well, if you are old-fashioned like me and still use a handheld calculator, there's generally a little function there, which in my calculator says y to the power of x. If you have a cell phone, nearly all cell phone apps, calculator apps have also got that function. The bottom left-hand box there, the screenshot there, they call it x to the y. That's on an iPhone. And then if there's something in between, you can use a computer, and on Excel, you can just put in that formula that I've got encircled there, A1, which is that cell, using that pointy arrow to the power of B1. So that's how you can calculate to the power of using Excel. So we said the flow from every dripper may not vary by 10% across the irrigation block. So for a 1 liter an hour dripper, what it means is we multiply that out. Now, if you take the calculation I showed you just now and you apply it, we want to find out what the pressure will be to get a flow rate of 1.05 liters an hour. And the same again, we want to find out what the pressure would be to get a flow rate of 0.95 liters an hour. And we can see if you calculate that out, that will be 11 meters and 9 meters respectively. So the maximum pressure will be 11 meters, and the minimum pressure will be 9 meters. So if we see our exponent is 0.5, flow variation is 10%. If we take the pressures that we just calculated, 9 and 11, 9 subtracted from 11 equals 2 meters. 2 meters divided by our pressure, our nominal pressure, which is 10 meters, is 20%. So what it means is that you can see that when our exponent is 0.5, for a 10% flow variation, we have a pressure variation of 20%. So what that means is our maximum pressure at the maximum point of our irrigation block will be 11 meters, and our minimum pressure can be 9 meters. So the difference in pressure from there to there will be 2 meters, and this we sometimes call the pressure envelope. Our next dripper. We take another dripper, and this one has got a lower value of x. It's only 0.4. So if we multiply that out, because the k will change a little bit. Whenever your exponent changes for a dripper, so too does the value of k. For a 1 liter an hour dripper, we have 0.3918 times 10 to the power of 4 equals 1 liter per hour. Now, if we calculate do that very same calculation now to get our maximum minimum flow rates, our maximum flow rate of 105 liters an hour, and our minimum of 0.95 liters an hour, where I'm pointing to now, that will result in pressures of 11.3 and 8.8 respectively. Okay, so our maximum pressure is going to be 11.3 meters, and our minimum pressure is going to be 8.8 meters. So now we can see when we have an exponent of 0.4, can have a flow rate of 10%, but now with our maximum minimum pressures being 11.3 minus 8.8, this is 2.5 meters. So 2.5 divided by 10 now gives a pressure variation of 25%. So we can see that if we have an exponent of 0.4, For a flow variation of 20%, of 10%, we will have a pressure variation of 25%. So you can see the relationship there. There's the comparison. X equals 0.5, pressure variation, 20%. X equals 0.4, pressure variation now expands to 25%. So the irrigation design must aim for 105 meters an hour, 11.3 meters pressure, down to 0.95 meters an hour, 8.8 meters pressure. So now our pressure envelope now is 2.5 meters. Now in part one, we discussed how as water travels along a pipe, it loses pressure, and we call friction loss. Now for a given flow rate, a small diameter results in more friction loss than a big pipe. Now what an irrigation designer does is he will now absorb that head loss from the maximum pressure to the minimum pressure by choosing pipe sizes of the submain and his lateral. Now I know the irrigation designers are watching this, so I'm just going to just make a note. It's not too important for the actual content of this webinar. In reality, it's more complicated than this. In reality, the flow rate is not constant along the submain. It's not constant along the laterals. The flow rate gets less and less and less down here, along here, until at the very end of the dripper line, we've only got the flow rate of one dripper left. Further, as the pressure reduces from friction loss, it is counteracted by a gain in pressure by the pipes going downhill. Now, all this does is to make the irrigation design equations more involved, but this is not an irrigation design webinar. For the purposes of this webinar explaining Q times equals K times P to the power of X, this isn't important. The minimum pressure nevertheless remains at the ends of the irrigation block and the maximum pressure at the beginning of the irrigation block. So an irrigation designer, he will choose his pipes to absorb the head loss from the maximum pressure to the minimum pressure along the laterals and the submains. The smaller the pipes, of the submains and the laterals, the more will be the head loss, and the less will be the cost. Smaller pipes, you can see that will create more head loss, and that if X equals 0.5, he will absorb 2 meters head loss. And if X equals 0.4, then it'll go up to 2.5 meters head loss. So therefore, the 2.5 meters we can see can actually use smaller pipes. So therefore, when X is 0.4, we'll use smaller pipes at a lower cost than with 0.5, X equals 0.5. There's more head loss to play with. We've got 2.5 meters versus 2 meters. So the lower the pressure exponent, the lower the value of X, the better. So if we want to keep, this is where we want to keep the head loss at 2. Okay, we've already seen that if we're going to keep the head loss at 2, if our exponent is 0.5, we've already seen the pressure, the flow variation will be 10%. But let's now keep those 2 meters, where instead of going to the 2.5 meters when our X equals 0.4, let's keep it at 2. What does that mean? Well, now, what flow rate? We know that we're going to have 11 meters here, and we know that we're going to have 9 meters here. What does that equate to in terms of flow rate? Well, we've got our equation, Q equals K times P to the power of 0.4, and that will result in a maximum flow rate of 1.04 liters an hour and a minimum flow rate of 0.96 liters an hour. So that flow variation now is 1.04 divided by 0.96 equals 0.08 liters an hour. So 0.08 liters an hour divided by 1 liters an hour, our nominal flow rate is only 8%. Okay, so we reduce it now from 10% down to 8%. Those 2 percentage points actually accounts for a 20% improvement in flow variation. So the lower the pressure exponent, the better. We have smaller pipes, less cost, and less flow variation. There is a third factor. I'm just putting a note here. When we combine this with the KD we haven't spoken about, we didn't speak in the last webinar, we're not going to speak about it now, but we will do it in future. When you combine it with this, you can actually, the lower the value of X, you can actually use longer laterals. But this is really needed. It's not discussed here because very rarely does a farmer station irrigation designer make the dripper lines as long as you possibly can. Normally the fields, your row lengths are set for you. Now when X equals 0, as we mentioned a few slides ago, anything to the power of 0 equals 1. So now, if we apply this to our equation, 0.316 times 10 to the power of 0.5 equals 1. Then, when we took 10 to the power of 0.4, we multiply that by 0.398, that also equals 1. But now if we have a look at the three lines at the bottom there, we've got three different pressures, 10 to the power of 0, 5 to the power of 0, and 40 to the power of 0. All of those figures, 10, 5, and 40, all to the power of 0 equals 1. Our value of K now becomes 1, so 1 times 1 equals 1, so it's 1 litre an hour. So for all three of those pressures, 10 meters, 5 meters, and 40 meters, regardless, the flow rate will always equal 1 litre per hour. And when we apply that to other flow rates, we can see that in the top, in the upper line there, 10 to the power of 0 times 2 is a 2 litre an hour dripper. 5 to the power of 0 times 1.5 is a 1.5 litre an hour dripper. And 25 to the power of 0 is 0.7. So you can see there that when X is 0, K actually becomes the flow rate of the dripper itself. Okay, and this is what we call pressure compensating drippers. In the last webinar, I was asked, with the turbulence coefficient, is it compulsory or is it obligatory? Are we as irrigation designers obliged to give the value of the turbulence coefficient? And my answer to that was no. And the reason was because as an irrigation designer, you don't really need that figure. I just showed it to show that we could compare drippers with drippers and the ability of those drippers to keep clean. However, with the exponent, with this formula, are we obliged? Yes. If we say that we meet International Standards Organization ISO 9261, and Netafim does manufacture drippers to this standard, then yes, we are obliged to give all the values of that equation. And now let's have a look at our competitors' drippers. In the last webinar, I showed you the classes of drippers, class 1, 2, 3, and 4. Classes 1 and 2 I gave as pressure compensating drippers. There's no point in going through pressure compensating here when we look at the exponent because the exponent is always 0. Okay. But with non-pressure compensating drippers, the Aries dripper has an exponent of 0.46, and if we look at our nearest competitor to that, they have an exponent of 0.48. So remember, the lower the value, the better. Now, if we look at our regular non-pressure compensating drippers, Typhoon Plus and Streamline X. Typhoon Plus, the exponent of both of those are 0.45. And then if I look at our manufacturer B, their large non-PC dripper has an exponent of 0.48. Their smaller one has got a value of 0.5, and the manufacturer barrel dripper is 0.52. That 0.52, earlier I said that generally the maximum exponent value is 0.5. They do actually sometimes go above 0.5. The old barrel-shaped drippers sometimes go above 0.5. So in this case, it's 0.52. And manufacturer C has an exponent of 0.46 and a 0.48. Now these are genuine competitors, drippers, and for those of you who want to actually have a look at and see the actual names and models of these drippers, our technical advisors can discuss that with you. So what is the value of all of this on the farmer? The value of this equation on the farmer, the lower the value of X, the smaller can be the non-specialized pipes. It's a lower cost to him. And it's a lower flow variation. So that means it's a more equal distribution of water and fertilizer throughout the irrigation block. On the irrigation company, what's the impact of this? Well, it means there's more ease and flexibility in the irrigation design to achieve that least flow variation. So in summary, the relationship between dripper flow rate and pressure, as we mentioned, this is the starting point of a hydraulic design of an irrigation system. The lower the value of X, the pressure exponent, the better. Smaller cost, low flow variation. In our next webinar, we'll look at the final two factors, which will be the KD and the filtration area. Well, thank you very much for attending. I hope that this webinar was useful to you. Take care and God bless.